as if you are standing in the pocket channel. So this is the area. This is a view from pocket channel upstream side to the downstream side. And what you see on the left hand side again further is the head regulator. And on the left hand side of it, we have the canal. So water from this river will be diverted into the canal through this head regulator. But how to prevent the entry of silt into this canal? So we utilize the concept that the silt concentration is high in the bottom layers. So what we do is we provide a silt excluder, which is provided in the form of a series of tunnels of reducing length as we move away from the head regulator. Okay, so yellow arrows represents the bottom layers which are having high silt concentration. So yellow arrows, the bottom layers basically enter into these tunnels, and on the downstream side of these tunnels we have provided under sluice gates. So we can operate those gates to control the quantity of water which is allowed to the downstream side, and silt along with these layers, this water also goes to the downstream side of the river. Okay, but the top layers or the upper layers which are shown in blue lines, so blue line does not mean that it is 100% free of silt. It is comparatively silt free, comparatively as compared to the bottom layers. So the concentration of the silt in this particular portion of the water is lesser as compared to the bottom layer, but the suspended sediment, suspended silt can still enter the head, this canal through these head regulators. The water is not crystal clear. It can be turbid also. Okay? That means sediment can enter into the canal also. The 100% elimination of the silt is not possible through any of the structures. But by utilizing this concept that the silt concentration is more in the bottom layers, so we can achieve cleaner and cleaner water in the canals. Okay. So this is the device category 1. We have already discussed about it. And this is the diagram which is given in the books generally for the silt excluder. Here you have the sill of the head regulator. These are the piers in which the gates will be running. You can regulate those gates to allow the quantity of water to be transferred. And here we have a series of tunnels which are going to the downstream side towards the under sluices. Okay, through these under sluices, we can control the flow of water through these tunnels. And this is the sectional view of those tunnels. Now, once the water has entered into the canal, there was only one device in the river, that is silt excluder. Because the water transfer is started at this point, and at the very first level, we provide silt excluder to exclude the silt from entering into the canal. But once the water has entered into the canal, so you can see this trapezoidal section of the canal. It is geometrical section, trapezium, and you can see that the length, along with the length, this cross section is maintained throughout. This trapezoidal section is maintained throughout the length. Okay, so this line is straight, or it can be a little curved depending upon the route of this canal that we decide, but generally it is kept straight in this fashion. So the water will be flowing in this way. Okay. So water will be flowing in this way. So this portion is called freeboard. This is the maximum water level that we can release into the canal, and the bank is a little above that. So this depth is called freeboard. But when the water has entered into the canal, along with the suspended silt, can we remove this silt also? So the answer is the next structure, that is structure 2. So how that structure acts, how that structure performs this task of removing the silt from this water which has already entered into the canal. The silt which has already entered into this canal along with this water, how to remove it? Okay. For this, let us see, this is the top view of the canal. Okay. This is the bed width. This is one side slope. This is other side slope. And on the adjoining area shown as green, this is the natural ground level. So this is the excavated portion of the river. Canal. If this is the canal, let us say that water is coming from left hand side and it is going to the right hand side. So we will be having a head regulator on this left hand side somewhere, and water is moving from left to right. So what we do is we depress the canal bed a little. So this is the depressed horizontal portion. We depress this bed over here. So this level is lower than the canal bed level. Okay. And to join these two levels, we have provided a inclined ramp. So it is not depressed all of a sudden. So from here, it is the canal bed. From here, it starts gradually going downward up to this level, and we maintain a horizontal depressed floor through up to this. And this is basically done in concrete to secure this depression of the bed and to secure this ramp also. We provide everything in concrete, with the concrete. Okay, concrete floor is provided in this station. And once we have this, depressed this bed also, we cut this one side bank at the same level. So this cut is also provided. So we cut one side of the bank. As of now, there is no water in it. Okay, we cut downstream, one side of the bank. Then we provide a wall of this shape. One thin wall is provided of this shape. Second wall is provided, third wall is provided, fourth wall is provided in this fashion. So they are low height walls, very thin walls, and their top level of these walls is little above the canal bed level. Okay, little above the canal bed level. So what you see is here the gap between the walls is very high. Here the gap between these walls is low. We can provide these intermediate walls also, which may not run up to this end, but they are provided in intermediate position and they run up to these points only, here, here, and here. Okay. So the water which will be going through this, they will be ultimately merging here. So here and here, that will be merging over here. Okay, so they are provided in this fashion. So the height of all these walls, the top level of the wall is at the same level, and that is a little above this canal bed level. Thereafter, we cover it with the concrete slab. Very thin diaphragm slab is provided on the top. It is covered on the top side. But you see here, we have not provided any slab. So the water in the bottom layer has the passage in this portion to move underside of the slab and go into these tunnels. Here also, we provide this concrete slab. The yellow lines, again, indicating the bottom layers with high silt content, they move along the bed, and here you can see they have entered below the diaphragm slab. So this slab, I have made this slab a little transparent so that you can see the these walls also. So where these flow lines are entering, and ultimately they are diverted here and go to the sideways. So the flow of water in the canal is here, but the bottom layers are segregated to move out of this canal. Okay. The top layers, they move to the downstream side just above the diaphragm slab. The top layers, they do not enter into this portion. The top layers move further. So the bottom layers can be separated out and they can be removed out of this canal. Okay. But how much quantity of water can be removed, should be removed? For that, we provide gates over here also. Like 3 gates we have provided for these 3 channels, 3 tunnels. So we can operate these gates and we can control the quantity of water to be released to the outward side. Okay. Now, once we have achieved this, we plug this excavated portion of the bank in this fashion so that now this channel section remains intact again. only the bottom portion has got some opening where the bottom layers will be entering into this portion, and they will be collected through this series of tunnels, and they will be taken to the outward direction. So this is called Silt Ejector. Okay. So this is the second category, Silt Ejector, and this is the diagram that is available in the books. You can see this is the canal. Here we have the gap. Some diaphragm slab is there. If you see this section AB, it is here. Some diaphragm slab is also provided at section AB. This is the canal bed level. It is depressed a little in this fashion. And in this portion, these walls are provided. So you can see these walls are very sharp. They are offering the bell mouth entry into the every tunnel, and ultimately the water is collected and ultimately released to the outfall channel.
Freight transportation is an absolutely essential part of modern life. Maintaining the complex supply chains of raw materials to finished goods requires a seemingly endless amount of hustle and bustle. Millions of tons of freight are moved each day, mainly on trucks and trains, but shipping got its name for a reason, and we still use ships to move a lot of our stuff. One of the main reasons is that it's efficient. In fact, moving a ton of goods the same distance on a boat takes roughly half the amount of energy than it would take by train, and roughly a fifth of the energy it would take on a truck. You can prove this to yourself pretty easily. Even heavy stuff is practically effortless to move around once it's floating on water. Of course, shipping by waterway also has its limitations. It's slow, for one, and not every place that needs goods is accessible by boat. We've overcome this obstacle somewhat through the use of constructed waterways, or canals. Canals and shipping are described in the earliest works of written history. But there's another limitation more difficult to surmount. Water is self-leveling. Unlike roads or rail, you can't put water up on a slope to get up or down a hill. Luckily, we have a solution to this problem. It may seem simple at first glance, but there's a lot of fascinating complexity to getting a boat up or down in a river or canal. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about locks for navigation. The efficiency of water transportation has a surprising amount to do with how the world looks today. Nearly every major city across the globe is located on a waterway, accessible by shipping traffic. Waterway transportation is weaved into the history of just about everything. So it's no surprise that even since thousands of years ago, humans have sought to bring access by boat to areas otherwise inaccessible. But creating waterways navigable by boats isn't as simple as digging a ditch. Unlike the open sea, the endless and uncluttered surface of water, land has obstructions and obstacles. The topography dips and rises, rivers and ponds get in the way, and man-made infrastructure like cities, roads, and utilities impede otherwise unhindered paths from point A to point B. The quintessential example of this is the Panama Canal, the famous cut through that narrow isthmus, saving ships the lengthy and dangerous trip around Cape Horn. At scale, this seems pretty straightforward. Just cut a ditch from the Atlantic to the Pacific. But the details of what is one of the largest civil engineering projects of the modern world are more complex. One of the most important of those details is that the majority of the Panama Canal isn't at sea level, but actually 26 meters or 85 feet higher. This is due to sheer practicality. Construction of the canal was already one of the largest excavation projects in history. Keeping boats at sea level would require cutting, at a minimum, an 85-foot deep canyon through the peninsula, involving millions and millions of tons of extra earthwork that would be completely infeasible. So, rather than cut the channel deeper, we instead raise the boats up from sea level on one side and lower them back down on the other. And we do this using locks, an ingenious and ancient technology that's made possible navigation on waterways and canals that otherwise could never have existed. The way a lock works is dead simple, and of course I have a little demonstration here to make this more intuitive. For a boat going up, it first enters the empty lock. The lower gate is closed, then water from above is allowed to fill the lock. This is usually done through a smaller gate or a dedicated plumbing system, but I'm just cracking the upper gate open. Once the level in the lock reaches the correct height, the upper gate can be fully opened and the boat can continue on its way. Going down follows the same steps in reverse. The boat enters the full lock, the upper gate is closed, and the water in the lock is allowed to drain. Again, I'm just cracking the gate in the demo, but this is often done through a slightly more sophisticated way in the real world. Once the lock is drained, the lower gate can be fully opened, and the boat can continue on. I hope you see the genius of this system. It's a completely reversible lift system that, in its simplest form, requires no external source of power to work, except for the water itself. One thing to notice about a lock is that even though boats can move through in both directions, water only moves through in one. The lock always fills from the upper canal and always drains to the lower canal. This is because gravity, hopefully that's obvious, but it's important to realize that even though we're not using pumps, the energy required to raise and lower boats through a lock isn't necessarily free. Each time the lock is operated, you lose a lock full of water downstream. And sometimes that matters. Canals aren't full of limitless water, and if there's a lot of traffic or the locks are particularly large, this could mean losing millions of liters of water per day. On large rivers, it's usually not enough to worry about, but in some cases this could cause a canal or reservoir to go completely dry. So, canals that use locks need some way to replenish the lost water, or at least limit how much water is lost each cycle. What if there was a way to save the water used to fill the lock and reuse it? On the Panama Canal, the locks use water from Gatun Lake, a critical source of drinking water for the country. During periods of drought, water supply becomes a serious issue. That's why when the canal was expanded in 2016, the new locks included water-saving basins. Like the locks themselves, these basins are an extremely simple and yet ingenious way to limit the amount of water lost each time the locks are filled. Let me show you how this works. On my demo, instead of draining the lock into the downstream canal, I can drain it partially into a nearby reservoir. Then, when the time comes to fill the lock, I can recycle the water from the basin, also called a side pond, to partially raise the level. Of course, I still need to use water from the upper canal to fully fill the lock, but it's less water than I would have used otherwise. In fact, if the water-saving basin is the same area as the lock, you can save exactly 1/3 of the water. The reason, again, is gravity. Water doesn't flow uphill, it always has to be going down. To be able to save water, you need a volume within the lock for it to come from, a lower volume for it to drain and wait in the side pond, and finally, an even lower volume within the lock for the saved water to go. That means the best you can do with a single basin is to save 1/3 of the water that would otherwise be lost. But it's possible to do better than this. One option is to have the water-saving basins have a larger area. Imagine an infinitely large basin so that no matter how much water drains into it, its level never rises. In this case, you could drain the upper half of the volume of the lock into the side pond, and then use that water to fill the lower half of the lock on the way up. So the area of the basin is important, with the larger area providing a greater water-saving benefit. The other way we can do better is to have more basins. Notice on the diagram that the bottom 2 volume divisions are lost each cycle. When the lock drains, each volume division moves from the lock to the side pond 1 division below, except for the bottom 2 divisions which are lost downstream. That water can't be stored in a side pond because the pond would have to be at or below the bottom of the lock. And when the lock is filled, each side pond fills the volume of the lock again 1 division lower. The top 2 divisions can't be filled from a side pond, so they're filled from the upper canal. It's pretty easy to see why more basins equals smaller divisions, and why that equals less water lost each cycle. Of course, for both the number of ponds and their area, there are practical limitations like how much land is available and the expense of all that plumbing. So you have to balance the value of saving the water in the locks versus the capital and ongoing expenses of constructing and operating these basins. That's made a lot easier with a pretty simple formula to calculate the ratio of how much water is used with side ponds versus without them. The new locks at the Panama Canal each use 3 basins, which are about the same area as the locks themselves. Plugging in 3 for the number of basins and 1 for the lock-to-basin area ratio, you can see that the new locks use only 40% of the water that would be required to operate without the basins. That's pretty impressive and definitely seems worth the cost of the basins. But it's not the only example of this. Another lock in Hanover, Germany has 10 basins, reducing the lost water by about 3/4, although the tanks are underground so they're harder to see. I've been talking about freight transportation in this video, but people use boats for all kinds of different reasons, and in the same way, there are all kinds, shapes, sizes, and ages of locks across the world. In fact, there are a lot of canals where you can operate the lock yourself. They're also not the only way to move a boat up or down, but that's a topic for another video. Next time you see a lock, consider where the water comes from, and keep an eye out for side ponds that help save a little or a lot of it for the next time. Hey, very quickly I just want to say this video was supported by viewers like you.